I give a hearty welcome to one and all gathered here, and I'm Alamailu from Vailtech Engineering College. My project mates are G. Nandini, S.B. Nasima, and our project guide is Mr. Mohammed Sulaiman, Assistant Professor of ECA Department, Vailtech Engineering College. Our project domain is VLSI, that is Very Large Scale Design, and our project title is An Efficient Adder Architecture for Process Variation. First of all, I want to explain you about what is process variations. Process variations are naturally occurring variation which cause changes in the channel width modulation. Channel width modulation is nothing but a space in between the electrons and protons to get attached to each other. When the channel width reduces, the circuit starts conducting more fastly and it starts heating. When the device starts heated up, the output will be a rapid increase and the output will not be the desired output. In order to avoid these process variations, we are designing this adder architecture. And these process variations are negligible under higher voltage conditions, which is above the subthreshold voltage. The subthreshold voltage of our designed adder architecture is in between 0 to 1 volt. The subthreshold voltage which we have designed is 0.7 volt. So we are going to operate this entire device under the 0.7 voltage, and then we are going to avoid the process variation. This is a short description of our project. Now we can enter into the abstract. This is the abstract of our project. Technological advancement lead to drastic changes in process variations. This in turn causes various performance related issues. In order to cope up with the process variation, particularly in adder architecture, we proposed an efficient serial full adder SFA design. The proposed adder is made to operate at subthreshold voltage. This method yields less performance degradations due to changes in process variations. However, the throughput will be of mediocre performance. It can be overcome by pipelined and parallel architectures. This pipelined and parallel architecture can be achieved by connecting a multiplexer along with the serial full adder design, which is done in our existing model. This is the implementation in the proposed model. The existing model is redesigned with the transmission gate and pass transistor logic. The transmission gate logic is used to reduce the power consumption, whereas the pass transistor logic can be used in the case of reduction in area. The implemented model can be used in complex arithmetic applications. Now we will give a brief description about the existing model. The existing model compared various adder architecture. It analyzed these different adder architectures based on throughput, latency, energy consumption, variation effects and other parameters. It proved that simpler architecture is less sensitive to process variations when operating at subthreshold region. However, it lacks in computational throughput efficiency. Literature survey. As we have explained earlier, we have analyzed totally 5 papers. Paper 1 is about analysis of KSA, SKA, CLA and RCA, and it proves that SFA is the best design. And paper 2 is about area efficiency. Paper 3 is about pass transistor logic under the subthreshold voltage applications. Paper 4 is about low power multiplexer design using pass transistor logic. Paper 5 is about implementation of 1-bit low power full adder based on multiplexer and pass transistor logic. This is the existing model. Single bit full adder in combination with flip-flop to do n-bit addition sequentially at different clock cycles. Here a multiplexer is attached along with a serial full adder and a D flip-flop is attached as a carry-in output of the D flip-flop. So first the multiplexer is used to do the parallel computation and the serial full adder is taken here because the architecture of serial full adder is simple and less when compared to the RCA. And the area of serial full adder is 16 times less when compared to the ripple carry adder. And the D flip-flop is used here to manage the delay, and the output of the D flip-flop is connected as a feedback to the multiplexer. A clock is given to the D flip-flop to operate under different clock frequencies. The carry output of the serial full adder is given as an input to the D flip-flop. The delay flip-flop is nothing but the output will be directly given as the input will be directly given as an output but with a small delay operation. The sum of the serial full adder is the output of the entire model. Our implemented model overcomes the disadvantages of the above mentioned existing model. It is implemented via pipeline or parallel design in simpler full adder architecture. Thus, it achieves higher throughput along with less sensitivity to the process variation. The transmission gate is used in carry section to observe the computational throughput. This proposed model consumes less power because the transistor count is less using pass transistor logic. This is the implementation of efficient full adder using transmission gate logic. Transmission gate is nothing but a bidirectional switch. It gives only 4 strong outputs, that is strong 0, strong 1, poor 0 and poor 1. There is no degradation of outputs as like of pass transistor logic. This is a pass transistor logic. Pass transistor logic gives 4 output, strong 0, strong 1, degraded 0, degraded 1. This degraded 0, degraded 1 is nothing but a swinging output. It will not be a strong output. So we will get a degraded output due to the voltage swing in pass transistor logic. This is the implementation of transmission gate using gate level implementation. And these are the outputs obtained under frequency curve, Fourier response curve and the input given to the transmission gate. This is the implementation of pass transistor logic serial full adder. And this is the output obtained based on the frequency curve, Fourier response curve and the input given to the transmission gate. And this is the comparative analysis which is made finally according to the power, current and voltage. The voltage under which the circuit is operating is 0.7 volt, that is a subthreshold voltage, and the current is 3.1542 nanoamps in TG and 2.5695 milliamps in PTL logic. The power consumption is less in transmission gate logic, that is 15.7712 nanowatts, and in PTL 12.8454 milliwatts. From this we can analyze that transmission gate logic has a reduced power and it will be the efficient method for designing a circuit which consumes less power. But if we consider in terms of area and the number of transistor count, PTL logic works good. Advantages of our proposed model: it is less sensible to the various effects due to process variations. The higher computational throughput is achieved in simpler adder designs. Since it operates under subthreshold voltage, it has better energy efficiency. The applications are arithmetic and logic unit, simpler element with advanced performance, well suited for low power devices. We have done 2 publications, design and analysis of an efficient adder architecture for process variation in the journal called International Conference on Contemporary Topics in Power Engineering and Aiding Technologies in Pondicherry Engineering College. And the paper 2 is about design of serial full adder architecture using FinFET logic. And the journal published is International Conference on Emerging Trends in Information and Communication, EMTIC 2017 in SA Engineering College. And this is the conference certificate which we have attached what we have got in the Pondicherry Engineering College. This is a consultancy letter. We have get a consultancy from Embedded Technology Solutions. Thank you.